Hi, my name is Callum Waters, student ID w1828868. This is my interim progression demonstration for my final year project at the University of Westminster, supervised by Cameron Javadi. Today I'm going to walk through my progress since the PPRS, milestone, stakeholder analysis, refined requirements, overall system architecture, algorithms used, updated time schedule, and what remains for the final system. I'll also highlight the key development decisions and how ethics has shaped the build so far. Mental health challenges among young people are significant and growing concern. According to the NHS Digital, 1 in 5 young people in England are estimated to have a probable mental disorder, and recent figures from papers highlight the number of young people lost to suicide. Despite this, early detection and access to support remain difficult due to stigma.
Just again.
Nah,
Are you sure?
yeah,
Yes, I
okay,
did.
excuse me. Long waiting times and limited resources. Digital systems can help address this gap by providing accessible, non judgmental early support. This project explores how artificial intelligence and machine learning can support early detection of mental health distress and ethically signpost users to trusted support services. Importantly, the system is designed for support and referral, not diagnosis or treatment. The original aim of the project was to develop a web-based mental health support application that uses natural language processing and machine learning to analyze user-provided text. The system aims to detect indicators of distress, anxiety, or crisis and provide appropriate responses and signposting to trusted services. Ethical compliance and user safety were core requirements from the outset, particularly given the sensitive nature of the domain. Followed supervisor feedback and ethical considerations were revisited and clarified. An overall system architecture was designed, a machine learning pipeline was implemented, and working web-based prototype was developed. Ethical safeguards and crisis escalation logics were also implemented and tested to ensure safe system behavior. Stakeholder identification onion diagram. The primary stakeholders are young users aged approximately 11 to 25. Their key interests include privacy, non-judgmental interactions, and easy access to help. These needs directly influence the design. No account creation is required, no personal data is stored, and responses are neutral and supportive in tone. Immediate escalation is triggered when crisis language is detected. Secondary stakeholders include mental health organizations such as the NHS, Samaritans, and Young Minds. Their interests include the accurate signposting, ethical handling of vulnerable users, and avoiding misinformation. As a result, crisis responses are predefined and deterministic, and generative AI is not used for crisis handling. Stakeholders include the project supervisor and the university ethics committee. The influence ensured strong ethical boundaries, including to diagnosis, no treatment advice, and no storage of identifiable personal data.
Why did you not say that?
Finally, wider stakeholders include public health services, society as a whole, who may indirectly benefit from early detection and prevention focused support systems. Overall, stakeholders need directly shape both technical and ethical design decisions. Ethical safeguards were prioritized over conversational complexity. Machine learning is used strictly for classification rather than diagnosis, and crisis responses override all other logic. Functional requirements were refined after PPRS feedback and categorized as implemented or planned. The prototype implements core functionality including text analyst, ML-based risk classification, crisis detection, ethical escalation, and support signposting. Planned features include controlled generative AI support for low and medium risk interactions, session-based processing, evaluation, and optional anonymous feedback. The non-functional requirements prioritize ethical safety, privacy, and reliability in the prototype. Emphasis is placed on anonymity is transparency and harm prevention. More advanced concerns such as scalability and security are planned for the final system but are not required to validate the core design at this stage. The use case diagram models how users interact with the system, including starting a chat session, undergoing assessment, and receiving escalation or support. Some use cases represent conceptual or planned functionality and are clearly identified as such. This slide shows traceability from aims to requirement, which is important for assessment. Early detection maps to FR2, FR3, and FR4. Ethical and safe user support maps to FR5 and FR1 and NFR3. Providing access to professional help maps to FR6, AI assisted decisions making maps to FR3, and planned FR7, privacy and trust map to NRF2 and NFR5. So requirements are aligned with the original purpose and ethical boundaries. What worked well is clear separation between core and extended features, ethical led design decisions, and machine learning classification validating feasibility. Limitations include smart database issuing effective generalization, database features not implemented in the prototype, and generative AI deferred for ethical reasons. Mitigations include clear scope definition, identifying future work, and incorporating supervised feedback. Now I'll present the overall system architecture. The system follows a layered architecture to support concerned user interface, machine learning services, decision logic, and external support. The prototype implements the core layers needed to validate functionality and additional components like OpenAI and aggregated evaluation are planned for the final system. This supports maintainability and ethical control. This figure visualizes the architecture. The front end handles interaction, the machine learning service performs reference, the decision layers applies safety and escalation logic, and external support represented when required. The key is the machine learning output informs behavior, but ethical safety overrides the remain deterministic. This slide breaks down components. The front end is HTML, CSS, and JavaScript. The back-end machine learning API is Fast API. The machine learning module uses TF, IDF, and logistic regression. Decision logic includes crisis override and risk gating. External links provide signposting. Planned final components include a database or analytics store for evaluation and OpenAI responses for low/medium risk only. In operation, the front end calls in the machine learning API via post/predict, receives risk and confidence, then applies decision to a rule to select a safe response. This highlights for data flow, user input is processed in real time, machine learning interfaces happens through a REST API. Only risk classification results are returned and no personal data is stored in the prototype. This supports privacy-first design and reduces ethical risks while still demonstrating core AI functionality. Here I justify the tech stack. Front end uses HTML, CSS, and JavaScript because it's lightweight, easy to prototype, and easy to host. Um, Backend uses Python and Fast API because it's effective for deploying machine learning modules as REST services and provides clean docs via docs. Machine learning uses scikit-learn with TF-IDF and logistic regression because it's interpretable, efficient, and suitable for text classification. Baselines, planned extensions are a database for aggregated evaluations and open AI integration for low/medium responses. The final system only. This slide clarifies what data exists and what is stored in the prototype. Inputs are processed in session. Interreference is real time. There are no accounts, no personal data persisted, and no conversations history saved. In the planned final system, only metrics are stored. Optional anonymous feedback may be collected, and no personal identifiers are stored. This directly aligns with ethics. The system remains privacy first while still enabling evaluation. This sequence diagram shows the end-to-end interactions. The user submits a message, the front end sends it to the machine learning API, the module produces risk and confidence, and the system applies decision logic to output either supportive response or crisis escalation and signposting. This diagram demonstrates how the components collaborate in real time. This is machine learning workflow used in the prototype. Natural language input is vectorized using TF-IDF. Then a supervised classifier predicts mental health risks, confidence scores, support decisions. Most importantly, the model is designed to support early detection and route users to appropriate support. It does not attempt diagnosis or therapy. The output influences system behavior rather than generating medical guidance. This class diagram represents a conceptual design of system entities such as sessions and assessments in the prototype. These structures exist only during the session and are not persisted to a database. The diagram is included to show planned structure and maintainability rather than to claim full data storage implementation. To summarize the algorithms used, the system combines supervised machine learning for risk classification, NLP for feature extraction, and rule-based decision logic for ethical safety and escalation. This hybrid approach ensures both technical functionality and deterministic safety. This slide documents the TF-IDF pre-processing algorithm. Its purpose is to convert text into numerical features and to classify key news by measuring how input a word is relative to dataset. Team frequency, term frequency measures how often a word appears. Inverse document frequency downweighs common word across documents, and TF-IDF is TF multiplied by IDF. It's suitable and it's well established. This slide documents the risk classification algorithm. Inputs are TF-IDF vectors. Outputs are risk categories such as low, medium, high, and a probability score used as confidence. Conceptually, logistic regression learns weights for features during training and uses a sigmoid function to compute class probabilities choosing the class with the highest probability. I chose logistic regression because it's interpretable, fast, and a common baseline for text classification in academic projects. Here I explain confidence. This module outputs a probability between 0 and 1% in confidence in predicted class. Confidence supports decision making, but decisions aren't made by machine learning alone. Thresholding helps reduce false escalations, especially with short or unclear inputs. This is important for mental health context, where you must minimize both over escalation and under escalation. That's why confidence is used alongside deterministic crisis rules. This is the ethical gating algorithm. Step 1, receive user text. Step 2, check for explicit crisis keywords like suicidal or self-harm. If detected, immediately escalate and signpost. If not detected, apply machine learning risk classification. If high risk and confidence is sufficient, escalate, otherwise provide supportive response. Rule-based logic is used because it ensures deterministic behavior, prevents unsafe responses, and provides ethical guarantees. So even if the machine learning is uncertain, the system remains safe by design. Now I'll summarize the updated time schedule and show how progress since PPRS aligns with what was planned. Completed since PPRS includes finalized requirements after supervised feedback, confirmed ethical compliance and exclusions, finalized the technology stack, designed the architecture, implemented the machine learning chatbot core, implemented crisis detection and escalation logic, and developed the front end prototype. So the milestone deliverables since PPRs are met and demonstratable. Changes since the original schedule include allocating more time to requirements, refinement, ethical review, prioritizing machine learning classification and safety logic before UL polish, deferring generative AI integration to the final stage and moving database and long-term analytics into future work. These changes were made to ensure the prototype remains feasible, ethically safe, and aligned with the project objective. This is a deliberate sequencing decision. Remaining planned activities include integrating controlled OpenAI responses for low/medium risk interaction, implementing optional anonymous feedback collection, UL refinements for usability and accessibility, further testing and evaluation of machine learning module, and final documentation and report writing. These items represent the path from a validated prototype to the final complete system. To conclude, this project has progressed from proposal to a working ethically bounded prototype that demonstrates real-time machine learning risk classification, deterministic crisis escalation, and trusted signposting. Next step focus on controlled generative AI for non-crisis support, further evaluation, and improved usability. Thank you for listening. I'm happy to answer any questions.